Hello everyone, and thank you for coming to see this webcast on schema-less table and dynamic schema. So just a brief introduction of myself. My name is Davide Mauri, and as you can hear from my accent, I'm from Italy. I'm the president of the Italian SQL Server user group, and I'm one of the solid Q members of the Italian subsidiary. I use it to speak to all major events, and still doing so, international and Italian one, and of course I do also consulting, training, and mentoring on everything is related to SQL Server databases engine and business intelligence. And this session specifically, it's on a really interesting topic in my opinion, which is a schema-less table, or how do you design a table when you don't know what it should contain in the future, and or maybe you know right now, but you know that it's also going to change the schema, so you need to handle dynamic schemas. So we will discuss about schemas, schema-less and implicit schemas, what are the meaning and what we can actually do to solve this problem, seeing some possible solution, and we will then go to the conclusion to see the pros and the cons of all the solutions we are going to see. So let's start first of all with the definition of the schema, which may seem obvious to everyone, but it's better to have a refresh on that, because today I think it's quite overlooked, because everyone feels the schema is something that restricts your free will to behave within a database or a data warehouse, but it's actually a very useful idea, because it's basically the definition of data structure that we know a priori. And of course it allows us to make sure that the data inserted into the table will be inserted only if it's compatible with the schema. So it allows us to prevent errors and to make the code of our application much easier, because we know what to expect. Of course, schemas are not only restricted to databases, because we can find schema also in XML, in programming languages like C# with classes or structures, or so object-oriented programming languages. So the idea of schema is not really related to the relational world, but it's really much more broader than that. So what schema-less mean actually? The idea is that with schema-less we say that we don't have the definition of the data we expect to have, so we actually really don't know anything about the data we are going to store anywhere we would like to store it, so in a relational database or somewhere else. And so it's always also defined as unstructured data, and we really have a lot of unstructured data. Just think about, text files or binary files, where basically there are no metadata and no position-based format that we can use to try to figure out what data is stored within. So actually, having a schema-less idea of our data, it's really not really useful, because we are actually in a situation where chaos reigns. So it's much better to have something a little bit different and more appropriate than the definition of schema-less, where it will be almost impossible to get the data out from our source. Usually we have, when we say schema-less, and when everyone says schema-less means that we have an implicit schema. So this means that in reality a schema always exists, even if it's implicit, so it's not explicitly declared. Without a schema, implicit or explicit, it will be completely impossible to handle data. So for example, the screenshot you are seeing right now shows a JSON document that tells us that we are looking at a song, Guns N' Roses song, and we know the album, we know the song name, we know the track number. Of course, this is kind of a very simple schema, but still is a schema. It's not a relational one, it's not strictly enforced, it's not an XSD, so an XML schema, it's not a structure, but still is a sort of a schema. And actually, this is not something I just came out by night, but this is the needing of having a schema, or more in general, the idea of having a schema is something that even Martin Fowler, one of the most well-known people in architectural design and programming, says that any data that doesn't fit into an implicit schema will not be manipulated properly, leading to errors. So this means that a schema must exist implicitly or explicitly. So even all the NoSQL or schema-less things are really saying that they are dealing with a implicit or dynamic schema, not without any kind of schema at all. The pros, of course, of having a dynamic schema or an implicit schema is that it's really, really easy to manage, because actually you don't have to manage it at all. You just use it, and that's it. You don't have to define the schema before you start to use it, so you can just start to define your schema as soon as you start to define your own data. It's really easy to be extended because you don't have to, again, change anything that has been declared before, because nothing has been declared before. So you just add new elements or properties or whatever, and you just have them to be ready to be used. And of course, it's easy to be used because especially JSON, but even XML actually, basically doesn't give you any problem in terms of mismatch between relational and object-oriented world. So it's really easy to take a JSON document or XML document and deserialize it into a class, and the opposite. So there are several pros of having an implicit schema. Of course, there are also some cons. And the main cons is that the schema information is hidden somewhere. So somewhere in the code base, and the bigger that your code base is, the biggest this problem became. All the metadata is scattered all across the code base, so it really becomes a nightmare to maintain it. Or if you don't want to go through this nightmare, you really have to be really, really good in order to make sure that all your developers uses a naming convention, stores all the schema in one single place, so it could be possible in future to make some changes and to maintain it. So we just have to avoid in a dynamic schema situation or an implicit schema situation where, for example, two developers doesn't talk to each other because maybe they are hundreds or 1,000 kilometers away, and they call in a different way the same entity or the same property, like customer name or customer underscore name. As you may imagine, this will make querying or data really, really hard, because we don't know where to look for specific information we are looking for. So we still need to have a sort of first normal form in order to avoid inconsistency and code inefficiencies. So we still need some schema, and it will not be maintained by an application like a relational database system, but it should be enforced through rules and naming convention and best practices. So we still need a schema, and of course, since this cannot be enforced physically by a software, it's going to happen that we forget about the best practices or the naming convention, and at the end we will have maybe two different ways to name the same property or the same entity. And this is something that in the long term will really impact the maintainability of our code. And again, regarding maintainability of our code or of our data, without an explicit schema, it's really, really difficult, if not impossible, to maintain integrity constraints. For example, you cannot say this column or this attribute must be an integer, because actually, since you don't define the schema before you start to use it, everyone can put into a customer name or a invoice value any kind of characters they want to put, so numbers or letters or whatever. So we are going to have big problems with data integrity if we cannot really enforce by applying the rules or by applying best practices within our team a good naming convention, a good approach to this implicit and dynamic schema. So without that integrity, the process of extracting information becomes really, really difficult, really expensive, and above all, untrustable. Because if you have 3 different columns containing, let's say, the customer name, and you only know 2 of them, you are going to miss some data in your report or in your queries or whatever. So data integrity is really a value that we should be able to preserve and really take care the preservation of integrity of our data. So the idea is that always Martin Fowler, so really the man that every developer look for to have answer, said schema-less means implicit schema means bad. Usually you should prefer an explicit schema because simply helps you to avoid all the problems we mentioned before. Still, there are some cases in which we cannot avoid to have a dynamic schema or an implicit schema simply because we don't know enough information, we don't have enough information on the data we are going to store into our system. Like, for example, an e-commerce website or a CRM or all this kind of solution that allows the end user to add new field and new structures after having deployed and configured the program. So there are some use cases for dynamic schemas, and of course there are also a lot of solutions, especially in the NoSQL database area that is really becoming well known and widely used in the last year. So are we going to use a document database or a key value store? Are we going to how do we integrate this new store into an existing application that maybe is already using our relational database and we are happy with that? And the problem is that integration doesn't come for free. So we are going to have some problems, or we have to develop some application in order to make sure that one data flows into another system and the other way around. So there could be interesting to understand and to figure out how we can manage schema-less or dynamic schemas within our relational database system, since I'm quite sure you are already using it for one reason or another. And of course the problem is that schema-less and relational database system are usually at the opposite extremes, because the database needs to have an explicit schema defined. This is what happens when you create a table, you actually define your own schema. And of course on the other side we have the schema-less idea, or the implicit schema idea, where we don't have a schema at all. But still, again, this is a very common request. So if we need to store that data, not only for doing pure persistence, so we also need to query the data in future and to aggregate it and to be able to search for the data. We are not just simply serializing and deserializing a class into a file or a storage, but we are really storing the data to do something nice in future. We have to solve this problem. And there are several solutions that people always use within a relational database system. There are the typical solution that is just simply adding a custom column, let's say custom column 1, custom column 2, and with the most generic data type you can use, like a string, for example, and that's it. Or there are some a little bit more sophisticated solution that came out in the last year with the improvement of relational database system, where we can store, for example, XML in relational database system, or JSON, or other complex columns, like columns that we create using a .NET data type. Or there is a very old but still good approach that defines how you should model your database if you don't know what it should contain in future. That is called Entity Attribute Value Models, or EAV, which is very common in ERP system or CRM system. It's quite old, but still really, really good in some cases, and we also discuss of this option. So let's start to talk about the custom column. Basically just adding columns, let's say customer 1, customer 2, or custom column 1, custom column 2. It was really the only option, but still the only also problematic one until 2008, because basically if you are going to add a new column to an existing table, even if that column doesn't contain any value, but you are adding that column to an existing table where you already have data, well, the problem is that that column is going to use space anyway, especially if it was an integer column or a datetime column, so not a var something column. So all the fixed size column will occupy space even if you are just storing null values, so and nothing inside. Just until 2008 this was a problem, as I said. From 2008, so from SQL Server 2008 and after, we finally have a nice option called the sparse column that allows us to add columns to an existing table, empty or not, doesn't really matter, and this column doesn't occupy space if they are not used. So this makes the table really, really easy to be modified, because basically even if your table is already full of data, the addition of this column, it is sparse column, it's really immediate. And in addition to that, if you have even 100 columns, all integers, and you are not using them, well, you are not even using space related to that column. So it really becomes easier to have a dynamic schema that we can add column anytime we need it, and without having to waste space or have the table locked to do all the updates of the existing row and so on. Changes to the schema must still be done with the alter table command, but this is not really a problem because the alter table command can be executed while the other people are using the table, so it's not going to block the table in a way that you need to put, let's say, a kind of an offline to do an offline operation, so it can be done online. It's really quick, so it really doesn't give any kind of problem in terms of concurrency and availability of your data. So sparse columns, this is the name of these features. It's really interesting because they are 100% columns. So from a application perspective, they are columns like any other column. And it's really interesting for the developer because all the sparse columns can be grouped together in one big XML column. So we can decide to use these columns like standard column, or to have all their value aggregated together into one XML column called column set. We'll see it later in the demo. And as I said before, if we are not using this column, they don't use any kind of space, so space is not wasted. The only downside of this is that when we store data inside this kind of column, the data uses a little bit more space than the usual one. So for example, integer occupy a little bit more than 4 bytes. I think it's 5 if I remember correctly. Anyway, there is a big table in the SQL Server help that tells you each column how much it takes more if it's a sparse column for the same data type you would have used for the normal column. So usually there is a kind of calculation to be made in order to understand if it makes sense for you to have a sparse column for that data type or not. Because of course it really depends on how much rows you will have set to nulls for that column, or how much rows will be used, will be using that column, and so they won't spare actually any unused space because you are going to use that column. So let's see this sparse column in action so you can get an idea of how it works. So I already created a database called Dynamic Schema, and now I'm going to create a classic product table. So this is a very standard product table with no special sparse column. And now I'm also saying, okay, since I'm going to create a table that will hold the products that I'm going to sell on my e-commerce website, I also need to have a table that contains all the possible attributes of my products. So I create a table called custom attributes, where here I put the attribute ID, the name of the attribute, and the data type. So I basically just a table that contains the name of the properties of the products I'm going to sell. And then here I create, in this case, I create a table that will contain the attribute of that product using using a column set and thus a sparse column approach. So let me create the table, and then I'm going also to do the same test, just using another option. I'm also using to save everything into XML. And now I'm creating the index just to make sure that my table is just as should be done. So with all the indexes and all the good stuff I should put on my table to make it perfect. And now here I create the table using the EIV approach that we'll see together later. So I'm just preparing my database for this demo and the next one. So let me create all the stuff here, and then I will be back to you. Just let me do this, and that's it. It's creating all my tables. You will see we are going to do a lot of tests. Okay, perfect. Now let's start to play with the sparse column. Here, in order to make everything quicker, I created a script that is going to add 100 columns to my sparse table, just because I don't want to create everything by hand. Okay. So now my table looks like something like this. So this is the table with the attributes. Of course, I haven't created any attribute yet, and here it is. But for each attribute, okay. Okay. So let me check that I did everything correctly. So, okay, I forgot one script. Here it is. Okay. Okay, so I'm saying that my product, all the product I'm going to sell will have the property name custom 1, custom 2, custom 3, and for each property I say this is a data, date property, this is a date field, this is another date field, this is a numeric field, this is a text field, and so on. So I just defined all the possible fields that my back office can use to define new product. Now I'm going to create the table I did before, but without having the correct data in place. Okay, perfect. Now if I do something like select from my my sparse my sparse column table, I can decide to select the single column, for example, and they will work just any other column, custom 1 or custom 2. Or I can simply try to do a select star, and this will return to me just one column that is the sum of all the sparse columns. So this is the column set. Just by looking at the table, you will see that we are going to have 100 columns here because I created a really huge table. So let me go to the sparse table. Here it is. So for SQL Server, this table has really a lot of columns. But they are all sparse, as you can see. So this means that if I'm not going to use that column, I'm not going to use the space related to that column. So let's do some example, and let me create the store procedure in order to fill this table with some random data so that we can also test for the speed and the performance of the various solution. And here we are. This one. Oops. Okay, here it is. Let me close all the stuff we don't need for the demo. Okay. Okay. So, for example, let me do something like this. Select from my sparse column table, select star from. As you see, it's empty. So now let's try to insert something, insert into my sparse column table. Let's say I'm going to insert the data for product 1, and product ID, and I'm using column 1 and column 1 and column 4, for example. Okay, I'm inserting some data for the column for the product 1, and the first column must be a date, as you can see from the definition of my schema. Let's say is today, so 0420. Oops, 0420. And let's insert also a number here, so it will be 10.8, for example. Okay, as you can see, my sparse table it simply behaves like any other table. The only difference here is that if I do a select star, since there is this column named column set, I simply get a result that is created by basically taking all the values for all the columns I used and putting them into an XML format. So this helps the developer to know the schema in advance, because each time I do a select star, I will know that all the non-sparse column will be returned, plus one big column, one big XML column that is automatically created by the system and contains all the values of all the other columns. Of course, I might also decide to access to the single column name, just specifying them by name exactly. So let's do custom 4, for example, from the table, and in this case my column will appear just like a standard column, so no XML involved anymore. So I can decide what is more comfortable for me, if to access to all the columns just looking at one big Excel that contains all the used data, or just accessing it specifying by name and just accessing to that specific column. So these are how I'm going to use my sparse column in a table. So just setting let me show to you the scripts. You just need to set the column to sparse, and that's it. Here it is. As you can see, you just have to specify the keyword sparse to say that that column is sparse, which means, again, don't use any space if there are no value inside. Otherwise, just use a little bit more space, and also be able to return both as a normal column or as an XML aggregated column. Okay, so now let's play a little bit with the possible solution we have to solve the problem. So we now have seen one of the features that SQL Server give us in order to solve this problem. The other option is to use the usual XML approach, so we can simply avoid to store data into columns and just storing everything into an XML, and that's it. Here performance could be good enough, but of course they are not optional, because XML is a little bit, not really toward performance, but it's a little bit more expressive, it's really flexible, but performance is really not the best point of XML. So it uses a lot of space, performance are not exceptional, but could be good enough, and this is another option that we have to store unknown schemas into our system. So just create a table with one XML column where you put inside everything you don't know in advance that can help you to store additional data you discover later in your application lifetime. Of course, XML needs performance boost in some cases because it's really too slow sometimes. So it would be nice if you can say, okay, this XML element that is saved into my XML document should be promoted to a real column, real relational column. Unfortunately, this is not something that will happen automatically, like it happens in some other databases. And you have to do it on yourself. So you can use triggers or service broker or doing it through your data access layer to read the value of an XML element or a property or attribute and store it into a relational column. So automatic promotion of XML element is not yet there. Of course, we could also be interested into saving data into a JSON format, since now it's really common to use to use JSON to store data. Unfortunately, support for JSON is completely missing from SQL Server right now, but we already know that Postgres already implemented it really well. So we can imagine that also, you know, the big names, SQL Server, of course, or Microsoft, Oracle, and all the other will come sooner. And so I'm quite sure that in the next release of SQL Server, we are going to have a native JSON support. Right now, we don't have it. So if you need to store JSON into SQL Server, you can just use or SQL CLR and basically encapsulate JSON in the management of JSON into a class that you develop and store into SQL CLR, so using .NET into SQL Server. There are some options here that you can also already find online. I've put two links to them. And of course, there is also just, this is more useful just for educational for purposes only. There is also a pure SQL solution that allows you to manage JSON 100%. Unfortunately, of course, the performance are not really optimal, so it's more for educational purposes, but it's really interesting to see how they solve this problem. And the last option that you can use to store your dynamic schema data into your relational database is just to store everything into a blob store, and that's it. So for example, just serializing your class into a binary format and storing it into a var binary column or into a JSON format again and storing it into a varchar column. Of course, in that case, JSON will just will be still unknown to SQL Server. It will be just a text file stored into SQL Server or a binary file stored into SQL Server. So we have several options to deal with dynamic schemas. So from sparse columns to XML to binary storage or blob storage into SQL Server. Of course, the main point is which is the best and which are the pros and the cons of everyone, and how we can decide which solution we should use in our environment in order to sustain maybe the performance we look for. So let's try to put this solution at test. I have created here a small application that allows you to hammer SQL Server with a lot of requests. So let me open the performance monitor first of all. And here we are going to measure the processor usage and the number of transactions and batch requests per second. And then here we are also going to execute this little application. Here it is. That allows me to do some tests. So we are going to simulate the creation of a new product into the table I've just shown you before. So we are inserting new product into our system. Of course, one product we use 3 custom attributes, another product we use another 5 custom attributes, and so on. So what we would like to understand here is what is the fastest way to store this product and to query them. And of course, querying the product is quite easy because basically all you are just extracting the product you are looking for, or you are looking for some specific attributes. So the idea here is to figure out how fast is the insertion of the product into our table, since this is probably going to be the most difficult things to do, since we don't know the schema in advance. So let's start with the sparse column. and let's see how many products we can insert into our system. So we are, oops, I forgot to start the performance counter. So we are inserting products for 10 seconds, and at the end of these 10 seconds, we are going to check how many product has been inserted into the system. So let me repeat the process again. Now running the performance counters, and okay, let's start and insert products in the sparse column table again. And as you can see here, we are able to do up to 500-600 batch per second, which is not really bad. And in 10 seconds, we inserted something like 6,000 products, which is really not bad for a virtual machine I'm using. So let's see what happens if instead of using the sparse columns, and as you can see here, let me now query some table. Here it is. So for example, let's extract some data from here. So these are my custom attributes, as I showed you before. Let's see how many products I have inserted. And the last time I created everything, so 5,800 and something rows. And so I also have inserted not only the product name, but also the product attributes. So just let's say product ID 9, and let's see which attributes has been inserted into my system. So products, I use the sparse column, so I'm using the sparse table where product ID equals 9. So here they are. This product has used the attribute custom 4, 7, 10, and so on. So of course, in real time, in a real solution, you won't have the attributes named column 4 and 7, but here will be, I don't know, number of CPU, screen size, or whatever, if this product you just save it in your system is a CPU. If it's a table, for example, you will have the width and the length, or if it's a car, you will have the drive type, the number of wheels, the number of seats, and all this kind of stuff. So it's really dynamic. Here you can store anything you want, and you don't even know in advance, because to add a new set of column here, we just have to do something like that. Alter table, add column, and as you see here right now, and this is really a metadata only operation. So I can do that while my system is still running. So let's try to again test the sparse column insertion. And while I'm doing the insertion of my product, I'm also changing the schema of the table. And as you can see, the application is still running perfectly. And you will see that the number of product that is going to be inserted will be very similar, here it is, to the one I inserted before. As you can see here right now, since this is a virtual machine that is also doing other stuff, now we've been able even to add even more product than before, so 6,000 and something. So the fact that we did 3 alter table while we was inserting really fast a high number of products didn't really impact the performance at all. So this is really a very nice use case for sparse column usage. Okay, so right now, if we do a refresh of my column, you will see at the end that I also have column A, B, and C that has been also inserted. So as you can see, the sparse column really helps us to have a dynamic schema, because I can easily change the schema, where for change I mean add new attribute, my new column to my table. And this really doesn't have any kind of impact in the performance and also in the space used by the existing rows here. So we used the sparse column, and we defined it, and I already have a Excel file here where we can start to save the performance of our solution, and you can see here I already did a lot of tests. But let's see here, for example, with a sparse column, let's see right now how many using we have here. This tool can be configured in order to choose how much stress you want to put in your database. So here we are using, let me show to you, here it is. Okay, we are using 32 tasks with a sleep time, so between each insert we are waiting for 10 milliseconds. And with that performance, I was able to insert up to 6,000 products in 10 seconds. So now let's try to insert an XML, the same data into an XML format. So let's use XML and let's see what happened. So I have 6,500 products inserted in 10 seconds by the sparse approach. Let's see how the XML approach behaves. As you can see, it's a little bit less than before because this is true. XML is more complex to be managed and slower. So in 10 seconds, using an XML document and so an XML column, we were able just to insert 4,000 instead of 6,000. So let's write this down here. So in 10 seconds on this machine with 32 tasks, with 10 seconds of sleep time, with the sparse column, we inserted something like 6,000, let's say 6,000 rows. With the XML, we've been able only to insert 4,000 rows. So it's quite a little bit much more slow. And if we query some data here, for example, let's query my select star from the XML solution where product ID equal 9, for example. Here you can see that now everything is still stored in XML. The format is a custom format that I decided to use. And even if it looks a little bit more compact than the one we saw before, that was generated automatically by the sparse, by the engine gathering all the sparse column, this approach is slower, is much slower, at least 50% slower than the sparse. Now let's see what happens if we, instead of using XML, we try to store a JSON document into a blob store. So let's try to use the JSON stored in a blob store. Let's see how are the performance. So we are just basically here while it works. Let me show you the table. We are storing everything into, here it is, a blob store where we just have a column that contains an char max where we store everything we want to store. So all the information about our product. And this works quite well because we are just using a varchar max column that has a really good performance. So here we are hitting 7,000, something like 7,000 products inserted per 10 seconds, which is quite good. The only downside of here, so let's say blob is 7,000. The only downside of this approach is that the blob is actually something that cannot be really easily managed while searching for some specific product attribute. Like, for example, let's try to do that. If I want to, let's say where product ID equal 9, just always use this product, for example. So here I stored a JSON, a serialized JSON, and it will be really hard here to extract all the product for which custom, the attribute named custom 60 has this kind of value. With the sparse column instead, I could do something like this. Where custom 60 is equal, for example, 1, 2, 3, 4. But since in the usage of a sparse column, you can also define the data type. We would know that this column is an integer column. So let me show it to you. So sparse, and we go to the 60. Here it is. So it's a numeric column. So we can also do something like between, or major, or greater than, or less than. So, and 999. This kind of query would be impossible on the blob approach, with the blob approach, because of course this blob doesn't give you any additional information on the type of the data it stores. So if you just need to do per system, this could work well. If you have to start to do some queries like just imagine it is not custom 60, the name of the attribute, but is the inches of the monitor, so just need all the LCD panels that are between 46 and 55 inches. This is going to be really hard to be done against a blob store, which is on the opposite, it will be going to be really, really easy to do on a normal column or a column store. So it's true that the blob store is a little bit faster, but we lose a lot in terms of flexibility and ability to easily query our data. Of course, instead of using the blob store, using a standard column, we could also try to use the file stream approach or the file table approach that are basically a variation of how SQL Server store the blob data, not only into a relational column, in a standard column, but using the file system. I leave to you, since we have not so much time right now, I leave to you to test everything, because you will see that they are not as fast as one can imagine, and so probably they are not the best approach to store binary data or text data into a SQL Server if you really need to write it fast. The other approach is to use, of course, the old one. The old approach is called entity attribute values. Here, there's a huge documentation on that kind of modeling. It's really used by a lot of systems. One of the most well-known systems that uses this approach is WordPress. And basically what you do is that you just store your entity fragmented on each column, and you say, okay, my entity ID, so it is, let's say that we are selling in our e-commerce even songs. So we have one row for each property of my entity. So my entity 1 has an attribute called album that stores this information, this value. So this means that each entity is scattered across more than one row, and while this makes the addition of new attributes really easy, because you just have to add a new row and that's it, it really makes the querying a little bit much complex, because of course you have to look on all the rows of that entity and not only on one. So it makes finding, for example, all the songs that as the author Guns N' Roses and the album is Appetite for Destruction a little bit more complex, because you cannot simply just write a simple where clause. You have to do a little bit more complex operation called relational division. So the entity attribute values, it's really, really flexible. It works perfectly, and these are the pros, of course, because it is really easy to implement. Unfortunately, it doesn't allow you to give some detailed control over data types. Usually, you just create string data types and that's it. Of course, you can find a kind of a balance here using the SQL variant or deciding to create several columns, one per type. But in general, you are a little bit constrained on how much control over the type you have. And as said before, there is a really complex pattern in order to implement end predicates, because it's not really easy to, again, query more than one line and take only the value that satisfies all the predicates. Luckily, the theory of the relational database helps us to solve this problem, because we just have to implement the relational division operator that is not available on all the major database systems. Probably only, I think it's only PostgreSQL implements it correctly. All the other systems like SQL Server, for example, doesn't give you natively the relational division operator. We have to implement it just following the theory, and here in the slides you will be able to download. There is the explanation on how the relational division works. basically, if we have this kind of table, which it's a generalization of the entity attribute value approach, we say, for example, here, we want to have all the rows that contain at least, for the same entity, just let me something here which will make it easier for you to understand. So, for example, here we want to have, we want to find all the product all the orders here that have the product 2, 3, and 400 as part of the order. So basically, we call the table that contains order and product the dividend, and the table that contains all the product we are looking for within the same order, the divisor. And what we expect to have from the relational division is the result. So are the only two orders that contains at least these three products, 200, 300, and 400. So just this is the general approach. As you can see, we can apply the same idea to our entity attribute value, because instead of looking for orders and product, we would look for entities and attributes. So extract all the entities that has at least these attributes, like LCD panel with it and CPU power, for example, if you are looking for a laptop. The theory tells us even how to solve the problem from a theoretical perspective using the relational algebra, and without going to explain in detail this formula, it's interesting to say that basically all these symbols here are one-to-one related to a SQL command, which basically is a select command. These are not exist or not in statement. So it's really easy to convert this formula into a query. And here you have the query. Here it is. Oops. Here it is. So it is a sample of how we can create a simple entity attribute value solution, and the query is, here it is. Something like that. The relational division can be implemented using basically a inner join, a group buying, and a having. This is the optimized version that really works well, and it's capable to search for specific entities that has some specific attributes in a table of more than 60 million rows in just a couple of milliseconds. So even if it seems to be quite complex, in reality it's at the end it's easy once you understand the logic behind, and can really have a really great performance. So it can really find entities in milliseconds time. So what we can do is also to try to find the performance of the EAV approach. So let's try to use a EAV approach to test our system and to see how good it goes. And you can see that using the EAV approach, we can even reach 1,000 and more batch transactions per second. So we are really inserting a lot of products here, and in fact we really are doing a lot of transaction, because for each product we are inserting 100 or dozen of rows, one for each attribute. This means that we are doing a lot of traffic, a lot of batch per second, but the number of products inserted is not so high, because of course it really takes time to insert all that values. The interesting stuff is that this approach that doesn't use any specific or any special data type like XML or varchar max or sparse type can be easily used with Hackathon and with the new in-memory engine of SQL Server. So if we change the table so that it's not a classic table but an in-memory table, so an Hackathon table, we can also create a storage procedure that does the insert and the querying into this table using a native compiled procedure. We can really have much better performance. because using hackathon and compiled procedures, we can really do a lot of insert per second. You will see right now. And as you can see here, we've been able to insert up to 5,800 prod per second. So we are basically at the same performance of the other option. So we can really have now a choice here, because maybe we are not interested so much into inserting rows very quickly, but we are more interested in retrieving the rows quickly, or keeping the CPU usage quite low, because this means that we can scale our system much better. So let's see again how much CPU is used with our system. So with hackathon, we are using 60% of CPU. So this means that we can improve the number of product inserted in this 10 seconds quite a lot. And in fact, here you have all the tests I did before preparing this session. And as you can see, just let me take the one that has a sleep time. Here it is. With hackathon and the entity attribute value approach, one on this machine can insert 18,000 products in 10 seconds. And of course, the sparse column is still the better approach, because it really allows us to leverage all the native optimization of SQL Server. But if we don't want to use the sparse column for any reason, and we still want to, or we have to stay within the EAV model, even the EAV model can be pushed to the limit, and reach the best performance that are sparse column solution and the blob format. Again, just remember that using the blob, you lose all the advanced query capabilities. With the sparse option or the EAV option, you are still able to look for some specific attribute or some specific value within your entity. So my advice, if it's possible, to stay within the sparse option or the EAV, and just use the JSON, so the blob option, only if you don't need to loop to search from some specific attribute within your entities. So here it is. As you can see here, you will also get this Excel file that shows you how much columns, how much product, sorry, can be inserted using the procedure I gave you, and you can use to make your own test to find which is the best option to store dynamic schema into a relational database. And again, we can really store and do a lot of insert per second, of product per second. So just remember, up to 22,000 product in 10 seconds can be inserted, which is quite a big number on this small virtual machine. This means that the solution can really scale quite well on bigger boxes. So we are almost at the end. So the conclusion, what are the conclusion of this solution? So everything works. In general, performance are more than good. So there are solutions that have really, really high performance, other solutions that have lower performance but are still good enough, because all the solutions tested were able to insert something like 5,000 products in 10 seconds. The only one that I strongly advise you to not to use is the JSON plus file table, because as you can see, it's really, really slow. So basically this means saving the blob into a file table structure, which is something new and available from 2012, and specifically use it to basically view a table, view a directory as a table, and the opposite. So it has some specific usage, but not for these problems, as you can see. And of course, you have to evaluate which solution is the best for you, because it really depends which kind of usage you need. You just need to search only for attributes. You only need per system. In this case, probably the blob solution is the perfect one. You need to look for attributes. Maybe the EAV is good enough. you need to look for attributes and values. Probably the sparse column is the simplest one. You need performance for reading, writing, or both. So with all the solution I presented, you can really create your own test laboratory and find the one that best suits your needs. So first of all, in order to conclude the session, let me say that it's really important to use dynamic schema only and only if we need it, because all the other options are faster. So if we need the schema in advance, let's stay with an explicit schema, as also Martin Fowler said, which is the best solution, not only for performance reason, but also to make sure we don't introduce bugs in our, or bad data into our system. So if you can use a schema, an explicit one, because all the data must be turned into information sooner or later, and with a dynamic schema, turning data into information, it's really, it can really be much more complex than just having an explicit schema. Any question?
I didn't see any questions in a questions tab. Maybe.
Okay, perfect.
I don't know.
So I will send to you.
Yeah.
I will send to you the slide and the demos, so you can put on your website, because of course in 1 hour I just did as you can see, as you saw, probably an overview of all the possibilities.
Yeah.
But they will have all the scripts that they can use to play and do a lot of tests on their machine to understand the best solution for them.
All right. Thank you very much. Thanks everyone.
Thank you for inviting me.
Thanks for coming. I will upload the recording to the YouTube channel and all the materials to the website, and you will get an email with all links. And thank you very much again, and see you next month.
Okay. Thank you. Bye-bye. Have a great day.
Bye.
You're welcome. Bye-bye.